Hello and welcome to this video. In this video we are going to be looking at the experiment looking at the force acting on a wire in a magnetic field. Now we're going to go back to an example that we looked at in one of the very first videos of magnetic fields, which was when we investigated this equation of F is equal to BIL. Okay, so this is the kind of equation that we're trying to investigate. Okay, so our goal here is not necessarily to find a value or anything like that. We're trying to prove that this equation is correct. Okay, because of course if we do all the maths and we get all the theory right, we have to then ensure that the experiment lines up with it, otherwise it's wrong. Okay, so what we're going to say is if we remember back to the very first video in magnetic fields, we started with a setup where I have a north and south magnets, something like this, where this is the north and let's say this is the south magnet, and this then has these uniform field lines that go this way, and I'm going to put this whole thing on top of a top pan balance. Okay, so this whole thing rests on this top pan balance, which reads the mass of what it is measuring. Okay, now I'm then going to say I need a current carrying wire to travel through this magnetic field, and that wire is going to go in like this. Now this wire then will be connected to some sort of circuit so I can have a current traveling through. So let me put a battery here. Now I'm going to refer back to this battery in a second to show if this is the correct orientation for this battery in terms of the direction that we want the current to travel. And I need to basically say in this experiment I need to investigate the relationship between either the force and the magnetic flux density, the force and the current, or the force and the length. Because I know for a fact that the thing that I'm measuring from this is the force. This is why it's on a scale, because it's going to tell me the mass, and I can calculate the force from knowing the mass. Now, in order to change the magnetic flux density, I would have to have either some sort of alternating current solenoid on this, and that's then going to need to be monitored with an oscilloscope, and that's going to get very long. We could alternatively have a different set of magnets which would have a different magnetic flux density. That is then going to take a while to then measure the magnetic flux density of each of them. The length of this, we would have to change the length of the magnets. So it comes down to the easiest thing for you to do in a classroom, in a lab, is to alter the current, really. So what we're going to say is we need to change the current. Now the way we're going to change the current is by changing the resistance through the circuit. So I have this variable resistor here, and I also need to measure the current. So I have an ammeter here, and that is then going to be connected to this. Now if I need this direction of the current, so I need to know which direction the current needs to travel for me to get an increase in the EMF reading. And from this, if I now take a top view, I have the north magnet here, I have the south magnet here, I have these uniform magnetic field lines going this way, and I have the current carrying wire traveling through the middle here. Now of course for F equals BIL I have to use the left hand rule, because this is a current producing a force, and I'm basically checking should my current be in this direction or should my current be in that direction. So for now I am not certain. So what I have to do is use my left hand rule, I know for a fact that the magnetic flux lines or the magnetic field lines go in this direction. I know for a fact, if this is a top view, I want my force to go down into this page. And if you line up your left hand with this, remembering this is FBI, so my force goes down into the page, my flux goes across. That means the current has to travel upwards like this. And therefore, I need my current to go in this direction, which means in this case, I need the current to go up here. Now we know current travels from positive to negative, so this is actually the wrong way around currently. So we need it to be the opposite way. So if we switch it, I now have the positive to negative side, and now I have some current traveling through here that is going to end up giving me a positive value on this scale. So what I'm doing is I'm going to vary the current and I'm going to measure the force. Okay. Now in order to do this, I am going to have to change the resistance of this variable resistor. So I need to alter the variable resistor such that I can read 6 different current and mass readings. 6 different current readings and 6 different mass readings. Okay, the corresponding mass readings. Now this then allows me to relate the current to the amount of mass that is felt. Now obviously I'm not trying to see how the mass is affected, I want to know the force. So we have to make sure that this scale is designed in order to measure gravitational force. So it's designed to measure weight force, which means we know from AS that the weight force is equal to mg. So if we have the mass, we're basically going to take all of these mass readings and multiply them by g to get the force. Okay. Then from this point we can make a table of these results where we have to specify what the current is in each of these cases in amps. Then we're going to have to record what the mass is in kilograms and then convert that into the force in newtons. Okay, so we can then say we'll get all of these values along with all of their errors, and we can then plot a graph here. And since we're interested in the relationship between force and current, we're expecting it to be proportional. So we've measured force, so that's going to be our y-axis, and we've controlled the current, so that's going to be your x-axis. And what you should find is you should get a dead straight line. Okay. Now the thing with this now is that if we were to make this in terms of the equation, I could say this is F times BLI, which means I have a form of y equals mx plus c would be the 0 point, which travels through 0, so I have no y-intercept. Now what this means is that the gradient of this graph is actually equal to the magnetic flux density multiplied by the length. And this can then be used to actually measure what the magnetic flux density between these two magnets are. Since the length is pretty easily measurable, so you could measure the length with a vernier caliper. And if you can measure the length with a vernier caliper, you can then use this method to calculate the magnetic flux density. Okay, so this experiment, the setup will always be the same. However, the outcome of the experiment, what you're actually trying to get at the end, whether you're just doing an investigation into the relationship to prove that it's directly proportional, or you are trying to calculate the magnetic flux density across these bar magnets, your setup will be the same, but your final result will be different. Okay, but both ways will follow the same method, and this is that method. Thank you for watching.